Hey, have you ever feel like the digital world just works like magic?
Yeah, it often seems that way.
Well, today we're pulling back the curtain a bit. We're diving deep into something absolutely fundamental that makes it all tick. Network architecture. Think of it like the hidden framework, the skeleton, supporting everything from your morning news browse to that, late night video call.
Absolutely. And in 2025, this framework for global communication, it's more vital than ever. Seriously, almost every single interaction you have online.
Streaming a movie?
Yep. Or accessing cloud docs, even your smart thermostat, checking the weather.
Yeah.
It all hinges on this often invisible design.
Okay, so our mission today, if you choose to accept it, and, well, you're here, so I guess you have, is to unpack the core ideas behind network architecture. We've got some excellent source material here, and we're going to filter out the noise, highlight the really crucial bits.
Yeah, it makes sense.
Yeah. Exactly. Make it clear, engaging, and maybe spark a few aha moments.
Right.
So to kick things off, the material points us to a really key question. What are the foundational concepts we need to sort of wrap our heads around? And it specifically brings up the OSI model.
Yeah.
Is it the deal with that?
Yeah, that's a perfect place to start. The OSI model stands for Open Systems Interconnection Model.
Yeah.
It's really a cornerstone for understanding how networks operate.
Good.
Developed by the ISO, the International Organization for Standardization, it's essentially a conceptual map. I like to think of it as a 7-layer cake.
A 7-layer cake. Okay, I'm listening.
Right.
Sounds potentially complex.
It can seem that way, but each layer has a very specific job in the whole communication process.
So what's the big advantage then of thinking about networks in these layers?
Well, the real beauty of this layered approach is that it breaks down something incredibly complicated network communication into smaller, more manageable pieces.
Right.
Each layer handles a specific set of functions. And crucially, each layer really only needs to talk to the layers directly above and below it.
Okay.
This standardization is super powerful. It allows hardware and software from totally different companies, different vendors, to actually work together, seamlessly. Like the application developer at the top doesn't need to worry about the specific type of cable being used way down at the bottom.
That makes a lot of sense. It creates a kind of modularity, doesn't it? So if something goes wrong,
exactly,
we can maybe figure out which layer is causing the headache.
Precisely. That's a huge part of its value. If your email won't send, thinking in terms of the OSI model helps you troubleshoot systematically. Is it the email program itself? That's layer 7. Could it be some kind of data formatting or encryption issue, maybe layer 6? Or is it an internet connection problem that points more towards layers 3 or 2?
Or even just a bad cable.
Or just a bad cable. Layer 1, yeah, it gives you a framework.
Okay, I'm ready to take a bite out of this 7-layer communication cake. Let's start at the top. Layer 7. What's happening there?
Right. Layer 7 is the application layer. This is the one you, the end user, interact with most directly. It's where your network-aware applications live.
Like my web browser.
Exactly. Your browser using HTTP or hopefully HTTPS. Your email client using things like SMTP, POP3, IMP.
Okay.
File transfer programs using FTP. Even the system your computer uses to look up website addresses DNS, the domain name system. That all happens at layer 7.
Got it. The stuff we actually see and click on. Okay, so once my browser, say, requests a web page, what happens next before the data even really starts its journey?
Good question.
Yeah.
That brings us down to layer 6, the presentation layer. This layer is all about the data's format and, well, presentation.
Okay, like making it look pretty.
Hey, not quite pretty, but making sure it's understandable. Its main job is to ensure that data sent from one system's application layer can be understood by the application layer on another system.
Translation.
Sort of, yeah. It handles things like character encoding, making sure text displays correctly everywhere, also data compression to make files smaller so they travel faster, and, really importantly, encryption and decryption for security.
So it's like the universal translator and the security guard for the data packet.
That's a great analogy, actually, yeah. Making sure everyone speaks the same data language and keeping secrets safe.
Okay, layer 6 handled. What's underneath that? Layer 5.
Layer 5 is the session layer. This one's all about managing the dialogue, the session between two applications.
Managing the conversation.
Exactly. It sets up the connection, keeps it alive while data is flowing back and forth, maybe handles things like checkpoints or synchronization, and then pairs down the connection gracefully when it's done.
Okay.
It can also play a role in authentication, proving who you are, and authorization, what you're allowed to do during that session.
Right, like logging into a website and staying logged in while you browse around.
Precisely that kind of function. It's the conversation manager.
Makes sense.
Okay.
4 layers down. What's next? Layer 4.
Now we get to layer 4, the transport layer. This is a really critical one. It provides end-to-end data transfer services between hosts.
End-to-end meaning from my computer all the way to the server, not just the next hop.
Exactly. And a key decision happens here. Reliability versus speed.
Ah, okay. How so?
We see this with the two main protocols at this layer. There's TCP, the Transmission Control Protocol. Think of it like sending a registered letter with tracking and delivery confirmation.
Very reliable.
Very reliable. It's connection-oriented, meaning it establishes a connection first. It ensures data arrives in the correct order, checks for errors, and manages flow control so it doesn't overwhelm the receiver.
Okay, so that's for important stuff where you need to know it got there intact. What's the alternative?
The alternative is UDP, the User Datagram Protocol. This is more like sending a postcard.
Quick and simple.
Quick and simple. It's connectionless. It just sends the data without setting up a formal connection first.
Yeah.
It's much faster because it skips all the reliability overhead of TCP.
But less reliable.
But less reliable. It doesn't guarantee delivery, order, or error checking. But that's fine for some applications.
Like what?
Streaming video is a classic example. Or online gaming. DNS lookups often use UDP too. In these cases, speed is more important, and losing a tiny bit of data here and there is usually better than introducing delays.
Gotcha. Reliable TCP for things like file transfers or email. Faster UDP for streaming or gaming. Okay, now we're definitely getting deeper into the network infrastructure itself, aren't we? Layer 3.
We are. Layer 3 is the network layer. This is where logical addressing and routing happen.
Logical addressing, IP addresses.
Exactly, IP addresses. Those unique numbers assigned to devices that allow them to communicate across different networks, across the internet. Layer 3 is responsible for figuring out the best path for data packets to travel from the source device to the destination device.
Like a GPS for data packets.
That's a pretty good way to think about it, yeah. It handles the routing decisions. The main protocol here, unsurprisingly, is IP, the Internet Protocol.
Okay, so hold on. You mentioned MAD addresses earlier at Layer 2 as physical addresses. Now we have IP addresses at Layer 3 as logical addresses. Why both? When does the network use one versus the other?
Yeah, that's a really common point of confusion, but it's crucial. Think of it like this. A MAE address is like the serial number etched onto the network card itself. It's permanent, unique to that piece of hardware, and used for communication within the same local network segment, like devices connected to the same Wi-Fi router talking directly.
Okay, local communication.
Right. An IP address, on the other hand, is like your postal address. It tells networks where you are located, logically, on the larger internet. It can change depending on which network you're connected to.
I see.
So when data needs to travel between different networks across the internet, routers use the destination IP address to figure out which network to send the packet to. Once the packet arrives at the final local network, then that network uses the destination MAC address to deliver the packet to the specific device.
So IP for the long-haul journey between networks, MC for the final local delivery.
You got it. Layer 3 and IP addressing are what make global internet communication possible. Without it, we'd just have isolated local networks.
That clears it up nicely. Okay, Layer 3 done. What's below that? Layer 2.
Down to Layer 2, the data link layer. This layer focuses on getting data reliably across a single physical link between two directly connected devices.
Like between my computer and my router. Or between two routers.
Exactly. It deals with the physical addressing. That's where the MAC addresses live. It takes the packets from Layer 3 and puts them into structures called frames. Its job is to make sure these frames get transmitted without errors over that one specific hop. Protocols you might recognize here are Ethernet for wired connections and Wi-Fi 802.11 for wireless. Those operate at Layer 2.
Okay. And I think the source mentioned sublayers here.
It did, yeah. Layer 2 is often conceptually divided into two sublayers. There's the MAC sublayer media access control, which handles how devices get permission to use the shared physical medium, like controlling who talks when on a Wi-Fi channel.
Right, prevents everyone talking at once.
Yeah, exactly. And then there's the LLC sublayer logical link control, which deals more with error checking and flow control specifically for that link and interfacing with Layer 3 above it.
Okay, almost there. We've hit the bedrock now, right? Layer 1.
We have. Layer 1 is the physical layer. This is the absolute foundation. It's all about the actual physical transmission of the raw bits, the zeros and ones, over the communication medium.
So the actual wires.
The wires, yes. Or the fiber optic cables. Or the radio waves for Wi-Fi or 5G. Layer 1 defines all the physical stuff.
Yeah.
The types of connectors, the voltage levels used to represent a 0 or a 1, the pinouts on the cables, the data transmission rates, bits per second. It's the tangible hardware aspect of the network.
Wow. Okay, so from my application clicking send all the way down through presentation, session management, transport choices, network routing, data link framing, and finally down to the physical pulses of electricity or light. That's quite a journey.
It really is, and it happens incredibly fast, millions of times a second.
That OSI model breakdown is super helpful. Now, you mentioned earlier, and our source highlights this too, that the TCP/IP protocol suite is more practically implemented. How does that relate to the 7 layers of OSI?
Yeah, that's right. While the OSI model is fantastic as a conceptual, theoretical framework for teaching and understanding,
The 7-layer cake.
a 7-layer cake, exactly. The TCP/IP suite is the set of actual protocols that, well, run the internet and most private networks today. It's a more pragmatic, real-world model that evolved alongside the internet itself.
So it doesn't have 7 layers.
It's usually described with 4 broader layers. The exact mapping to OSI isn't always a perfect one-to-one fit, and different textbooks might show slightly different interpretations, but generally.
Okay.
TCP/IP has an application layer at the top, which corresponds roughly to OSI's application, presentation, and session layers. Layer 7, 6, 5.
Got it. Bundles the top 3.
Then there's a transport layer in TCP/IP, which maps directly to OSI's Layer 4 transport layer. That's where TCT and UDP live.
Okay. Same name, same function.
Then the TCP/IP internet layer corresponds to OSI's Layer 3 network layer. That's IP's home turf.
Right.
And finally, TCP/IP has a network access layer, sometimes called link layer or network interface layer, which combines the functions of OSI's data link and physical layers, layers 2 and 1.
Ah, okay. So a bit more condensed, but covering the same ground functionally. OSI is the detailed theory. TCP/IP is the practical implementation based on a slightly simpler plan.
That's a great way to summarize it. OSI helps us understand what needs to happen. TCP/IP provides the actual tools, how it happens on the internet.
Okay, so within that TCP/IP suite, what are the absolute key players, the main protocols we should know? You've mentioned some already.
Definitely. At the heart, as we said, is IP, the internet protocol, doing the logical addressing and routing, getting packets across networks. It's connectionless and considered best effort or unreliable on its own.
Right. It needs help.
It needs help from the layer above, usually. That's where TCP comes in, Transmission Control Protocol, providing that reliable, connection-oriented, ordered, error-checked delivery. Essential for web browsing, HTTP, HTTPS rely on it. Email, SMTP, POP3, IMAP, you rely on it. File transfers, FTP relies on it.
Okay. And the alternative?
UDP, User Datagram Protocol, the faster, connectionless, but less reliable option. Good for streaming, online gaming, DNS lookups, as we mentioned.
Got it. What else is critical?
Well, up at the application layer, relying on TCP or UDP, we have a whole host of essential protocols. HTTP and its secure version HTTPS are fundamental for the World Wide Web.
Can't browse without them.
Exactly. DNS, the domain name system, is critical for translating the website names we type, like www.example.com, into the IP addresses computers need.
The internet's phone book.
Right. Then the email protocols, SMTP for sending mail, POP3 and IM for receiving it. And FTP, the file transfer protocol for moving files around, though it's maybe less common for end users now than it once was. It's really the combination of these open, standardized TCP/IP protocols that has allowed the internet to grow and connect the entire globe.
It's pretty amazing how all these invisible pieces work together. Okay, let's shift gears slightly again. Our source material also brings up network topologies. What exactly are we talking about there?
Network topology refers to the arrangement or layout of the network devices, computers, switches, routers, and how they're connected. It's like the architectural blueprint of the network.
Okay. And does it describe the physical layout or how data flows?
Both, actually. That's an important distinction. We talk about physical topology, which is how the cables are actually run and devices physically placed. And we talk about logical topology, which described how the data signals actually travel across that physical layout. Sometimes they're the same, sometimes they're different.
Interesting. So why does the topology matter?
Oh, it matters a lot. The choice of topology significantly impacts things like the network's cost, how easy it is to install and manage, how well it scales if you need to add more devices, its overall reliability and fault tolerance, and its performance.
Right. Different layouts have different strengths and weaknesses. What are some common ones we might encounter?
Well, historically, one of the simplest was the bus topology. Imagine one long cable, a bus, and all the devices just tap into it.
Sounds simple.
Simple to set up initially, yes. But it had major drawbacks. If that main cable broke anywhere, the whole segment went down.
Single point of failure.
Big time. And performance degraded quickly as you added more devices because they all had to share the same cable bandwidth. You really don't see pure bus networks much anymore.
Okay, so probably not the best for reliability. What's another older one?
There was also the ring topology. Here, devices are connected in a closed loop, like a circle. Data typically travels in one direction around the ring from device to device until it reaches its destination.
Does that solve the single break issue?
Not necessarily. A single break in the ring could still bring down the network, although some ring technologies had built-in redundancy mechanisms. It could handle traffic a bit better than a bus sometimes, but it was complex to manage and remove devices. Also not very common today on LANs.
Okay, linear and circular seem a bit fragile. What became more popular?
That leads us to the star topology. This is probably the most common one you'll find in modern local area networks, LANs, like in homes and offices.
How does that work?
In a star, all the devices, computers, printers, etc., connect directly to a central point. Originally, this might have been a hub, but nowadays it's almost always a switch.
Right, the box with all the blinking lights my router plugs into.
Exactly. The switch acts as the central connection point. This layout is much easier to manage. Adding or removing a device is simple. Just plug it in or unplug it from the switch. And troubleshooting is generally easier. If one cable or device fails, it usually only affects that one device. The rest of the network keeps working fine.
That sounds much better. Is there a downside?
The main downside is that the central switch itself becomes a single point of failure. If the switch dies, everything connected to it loses network access. But switches are generally pretty reliable these days.
Okay, star seems like a good balance for typical LANs. Are there setups designed for even more reliability, maybe for bigger networks?
Absolutely. That's where mesh topology comes in. In a full mesh, every single device has a direct point-to-point connection to every other single device.
Oh, that sounds complicated and expensive.
It's extremely. Imagine cabling every computer to every other computer in an office. But it offers incredible redundancy. If any one link or even several links fail, there are usually multiple alternative paths the data can take.
So maximum uptime.
Maximum uptime. Because of the cost and complexity, full mesh is rare. More common is a partial mesh, where only the critical devices, like core routers or servers, have multiple connections to other key devices, creating redundancy where it's needed most.
Yeah.
You often see mesh topologies used in the backbones of large enterprise networks or the internet itself.
Right, connecting the main hubs reliably. Makes sense. Are there any other main types?
The last main one is really just a combination, the hybrid topology. This simply means using two or more different topologies together.
Like connecting several star networks together.
Exactly. Maybe you have several floors in a building, each wired as a star network using switches. Then those floor switches might be connected together using a high-speed bus, or maybe a partial mesh backbone running between floors. Most large networks end up being hybrid in practice.
Okay, so bus, ring, star, mesh, and hybrid covering the physical layouts. And remembering the logical flow might be different. That's a good overview. Now, looking ahead, our source material talks about the trends and challenges really shaping networks in 2025.
This stuff is evolving fast, right?
Oh, incredibly fast.
Yeah.
Network architecture is constantly adapting to new demands and new technologies. A huge driver is just the relentless need for more bandwidth and speed. Tell me about it. Everything seems to need more speed.
Doesn't it? Think about the explosion of 4K and 8K video streaming, the shift to cloud-based everything, online gaming, and now emerging things like AR and VR. They all consume massive amounts of bandwidth.
Right.
So this is pushing the development of faster Ethernet standards. We're talking 400 gigabit, even 800 gigabit Ethernet in data centers. We've got newer Wi-Fi standards like Wi-Fi 6, 6E, and now Wi-Fi 7 rolling out, offering much higher speeds and better performance in crowded areas. And, of course, the ongoing global deployment of 5G cellular, with research already well underway for 6G. The hunger for speed is just constant.
It really feels insatiable. What else is forcing big changes in network design?
Another massive factor is cloud computing and the move towards network virtualization. So many businesses and individuals rely on cloud services now. This demands networks that are incredibly flexible, scalable, and automated.
How does virtualization help there?
Technologies like SDN software-defined networking are key. SDN separates the network's control logic, the brain, from the underlying hardware, the muscle. This allows network administrators to manage and configure the entire network centrally using software, making it much more agile.
Okay, so more software control.
Exactly. And related to that is NFV network functions virtualization. This takes network functions that traditionally required dedicated hardware boxes, things like firewalls, load balancers, routers, and turns them into software that can run on standard servers.
Ah, like virtual machines, but for network gear.
Precisely. So instead of buying and racking a physical firewall appliance, you can spin up a virtual firewall instance in software. This provides huge flexibility, cost savings, and makes it easier to scale services up or down as needed. Very important for cloud environments.
Right, makes the network infrastructure itself more cloud-like. Okay, what other big trends?
Then there's the elephant in the room,
Right.
the Internet of Things, or IoT.
Billions and billions of connected devices.
Exactly. We're talking smart home gadgets, industrial sensors, connected cars, wearables. The sheer volume is staggering. This presents enormous challenges for network capacity. How do you handle all that traffic? Also, security is a massive concern with IoT, as many devices are low power and have limited security capabilities. And just managing all these devices is complex. Often, IoT requires specialized network architectures and protocols designed for low power consumption and handling potentially intermittent connections.
Yeah, securing that many potential entry points sounds like a nightmare.
It's a huge focus, which leads directly into the broader challenge of network security in general. It's not really a trend so much as a constant escalating battle.
The threats just keep evolving.
They really do. Cyberattacks are becoming more sophisticated all the time, so network architectures have to be designed with security baked in from the ground up. We still need the traditional tools, firewalls, intrusion detection and prevention systems,
Idiocy.
VPNs, but increasingly, AI and machine learning are being used.
AI for security.
AI can analyze vast amounts of network traffic data to identify subtle patterns or anomalies that might indicate a new or disguised attack, often much faster than human analysts can. It's about proactive threat detection and automated response. It's becoming essential.
Fascinating. Okay, what about mobile? You mentioned 5G and 6G earlier.
Right. 5G is already transformative, and 6G is on the horizon. 5G isn't just about faster phone downloads, although it does that.
Right, there's more to it.
Much more. It enables 3 key things: enhanced mobile broadband, eMBB, that's the faster speed, massive machine-type communications, MMTC, connecting potentially millions of low-power IoT devices per square kilometer, and ultra-reliable low-latency communication, URLLC.
Okay, that last one sounds important. Low latency.
Extremely low latency, meaning minimal delay. This is critical for applications where near-instantaneous response is vital. Think remote surgery, controlling autonomous vehicles, real-time industrial automation. 5G's URLLC capability opens doors to things that just weren't feasible before. And 6G, while still in the research phase, promises even faster speeds, potentially lower latency, and maybe integrating AI more deeply into the network fabric itself, enabling entirely new capabilities.
The low latency part really changes the game for real-time control applications. What other architectural shifts are happening?
Edge computing is another major one. This is kind of the opposite of centralizing everything in the cloud.
Bringing computing closer.
Exactly. Moving processing power and data storage closer to where the data is actually generated and used at the edge of the network, near the sensors, the devices, the users.
Why do that?
Primarily to reduce latency. If you have an autonomous car making split-second decisions, you can't afford the delay of sending sensor data all the way to a distant cloud server and back. Edge computing allows for faster local processing. It also reduces the amount of raw data that needs to be sent over the network backbone.
Makes sense for things needing quick responses.
Definitely. But it requires new distributed network architectures to manage these edge resources effectively and securely.
Right, more complexity again. Any other key trends from the source?
One more really interesting one, particularly tied to 5G, is network slicing.
Slicing, like cutting up the network.
Sort of, but virtually. It allows network operators to take one physical network infrastructure and create multiple virtual end-to-end logical networks on top of it. Each slice can be independently configured and optimized for specific needs.
How so? Give me an example.
Okay, so on the same physical 5G network, an operator could create one slice optimized for ultra-low latency, maybe for a cloud gaming service or industrial control. Another slice optimized for massive device connectivity for handling thousands of smart meters. And a third slice optimized for high bandwidth for mobile video streaming.
So you tailor Virtual networks for different jobs, all running on the same hardware?
Exactly. It provides incredible flexibility and efficiency. Instead of a one-size-fits-all network, you can deliver customized network characteristics based on the application's actual requirements.
That sounds potentially game-changing for how services are delivered. It prompts a thought. Consider how this kind of network slicing might really change how we access and pay for different types of online services in the future based on their network needs.
That's a really interesting implication, yeah. Custom quality of service tiers becoming much more granular and application-specific.
Okay, one last trend mentioned was quantum networking. That sounds futuristic?
It is definitely still in the early research stages, but the potential is fascinating. Quantum networking aims to use principles of quantum mechanics, like entanglement, to transmit information. One of the most promising near-term applications is for security, particularly quantum key distribution, QKD, which could offer fundamentally unbreakable encryption. But it's very early days.
Wow. Okay, so bringing it all together then, after exploring the models, the protocols, the layouts, and these cutting-edge trends, what's the big takeaway? What's the overarching importance of network architecture in, 2025 and beyond?
I think the core message is that network architecture is truly the invisible, indispensable foundation of our modern digital world. It's not just technical plumbing, it's the enabler.
Right.
Everything we've discussed, from the basic OSI layers and the workhorse TCP/IP protocols to how we physically arrange networks with topologies, it all governs how effectively, reliably, and securely we can communicate and share information globally.
It connects back to everything we do online.
Everything. And it's not static. The constant evolution we see, driven by cloud, IoT, 5G, security needs, edge computing, virtualization, even quantum research, it's all about building a network infrastructure that's smarter, faster, more scalable, more secure, and more adaptable.
To keep up with our demands.
Exactly. To support the ever-growing and ever-changing ways we live, work, and interact in this interconnected society. Understanding at least the basics of network architecture is becoming important for almost everyone who uses technology. And honestly, the future of how we connect and innovate really hinges on the continued development and smart design of these underlying networks.
It really is the silent workhorse powering so much of our daily existence.
Well, thank you. This has been a fantastic deep dive into the often complex but absolutely vital world of network architecture.
My pleasure. It's a fascinating field, constantly changing.
We covered a lot: the OSI model, TCP/IP, those topologies, and some really important modern trends shaping where things are headed.
Hopefully it demystified some of it.
I think it did. And thank you, our listener, for joining us on this exploration today. We really hope this shed some valuable light on how our digital world is built and connected.
Yeah, thanks for sticking with us through the layers and protocols.
Thanks again for tuning in to the deep dive. If you found this discussion insightful, please do consider subscribing to our channel. We've got more deep dives into important tech topics coming up.
We'd appreciate that.
And if you know someone else who's curious about this stuff, maybe share this with them. Your support genuinely helps us grow the channel and reach more people. We really appreciate you spending your time with us today.